tonight's journey drifts into the densest stars in the cosmos: neutron stars, pulsars, magnetars, tiny worlds of extreme gravity and precise repeating signals. In the next chapters, calm scenes unfold from surface glow to sweeping beams, from slow spin down to magnetic storms. If this kind of quiet science helps you rest, please like this video, subscribe, and turn on notifications so new sleep documentaries appear right when they're needed. This is Universe Documentary for Sleep. Now the universe grows quiet and the story begins. A star can end in a way that leaves almost nothing to look at, yet almost everything to measure. The core that remains is a neutron star, a compact object, where matter reaches extreme density and leaves clear signals. In a wide field of thinning debris, faint filaments drift outward and cool. At the centre, a small dark sphere sits in stillness. Its edge is sharp against the surrounding haze. Light near that edge bends in subtle arcs. The scene feels quiet, yet the physics inside it is anything but quiet. The scale begins with a star's vast radius. It narrows to a remnant that fits inside a region no larger than a city. A diameter of about 20 kilometers is enough to hold more mass than the Sun. That size is like crossing a major city from one side to the other. The mass is like the entire Sun compressed into that span. This contrast is the first stable anchor. Density is not a detail here. Density is the point. A simple comparison makes the idea easier to hold. A long shelf of books becomes a single brick when squeezed without leaving gaps. The shelf length disappears, the weight remains. In that same spirit, a large star's core loses volume while keeping mass. The pressure rises until ordinary structure cannot survive. At this distance, the remnant is not seen as a glowing surface with texture. It is seen as a boundary between regimes. Outside gas expands and thins. Inside matter packs so tightly that familiar intuition stops working. A payoff arrives early and quietly. A neutron star is not held up by heat. It is held up by the rules that limit how tightly particles can be forced together. The collapse begins in a dying, massive star. Fusion in the centre stops providing enough outward push. Gravity takes over. Layers fall inward. The inward motion accelerates. In seconds, densities climb beyond the point where atoms remain intact. A second visual anchor forms in the mind. A falling column of fog narrows into a dense, smooth plug at the bottom of a valley. The fog is the outer layers. The plug is the core. The boundary between them is a thin front that moves fast. It is not a sharp wall. It is a steep gradient. Matter crosses it and changes character. A term appears defined in plain shape and then released. Neutron degeneracy pressure is a quantum crowding limit that resists compression. Like a crowded theatre that cannot fit one more seat available, states fill and force a new arrangement. Like grains in a sealed jar, motion becomes constrained when there is no space left. This matters because it provides support without needing high temperature. The support is not a spring. It is a rule. That rule holds a neutron star against gravity, at least up to a point. The world outside the remnant keeps changing. The expanding debris forms arcs and knots. Thin sheets of gas fold into ripples. Dark lanes cut across brighter regions where cooling happens at different rates. The centre remains small. The contrast between the outer cloud and inner sphere becomes another unlock. The outer layers are about motion and diffusion. The inner object is about structure and constraint. A neutron star is often described as a solid sphere. That is only partly true. It is better imagined as layers with different behaviours. The outermost region forms a crust that is rigid. Below it, matter can flow in ways that resemble fluid. Deeper still, matter behaves in a regime that has no everyday counterpart. Even before those details, one physical feature stands out. The surface gravity is so strong that the atmosphere is extremely thin. The transition from surface to vacuum happens over a very small height. A cliff in density sits at the boundary. This sharpness shapes how radiation leaves the object. It shapes how light scatters near the surface. It shapes how heat spreads across the skin. Another quiet payoff arrives. Many signals from neutron stars are shaped more by geometry than by brightness. A small hot region on a rotating sphere can create a repeating pattern. A strong magnetic field can guide charged particles into arcs. A slight asymmetry can add a tiny wobble that becomes visible far away. In that region, light behaves as a precise messenger. It carries timing. It carries energy distribution. It carries modulation. It carries hints of the surface shape even when the surface itself is unresolved. A third visual anchor drifts in. A dark sphere rotates slowly in a cold void. A thin band of faint glow lies around it, not as a ring of matter but as a belt of emission. The belt looks brighter at some angles. It looks dimmer at others. The brightness changes without drama like a distant beacon muffled by haze. The motion is steady. The pauses feel long. The impression is calm, yet that belt is a clue. Rotation can be fast, magnetism can be extreme. The combination can make the object act like a cosmic metronome. The script does not need a machine, a telescope, or a screen to make that idea vivid. A signal would arrive as a repeating whisper in radio waves. Another signal would arrive as a pulse in higher energy light. The repeating structure is the measurement. The repeating structure is the handle for inference. Here a limit of intuition appears softly. No direct view reaches the interior. No image resolves the layers like a cut stone. The core is hidden behind a surface that is only tens of kilometers across. Distance smears it into a point. Even close by cosmic standards, it remains too small for direct mapping. The interior must be inferred from indirect traces. Timing can show spin changes. Energy patterns can hint at temperature gradients. Orbital effects can reveal mass. Yet the equation of state, the exact relation between pressure and density inside, remains uncertain. Models compete because the same outer behavior can come from different inner arrangements. This is not a failure of effort. It is a boundary set by physics and distance. Another payoff fits into that boundary. Neutron stars become laboratories because their signals are clean. They repeat. They drift in predictable ways. Small deviations matter. A tiny change in spin can suggest a shift in internal coupling. A modest change in surface emission can suggest a new hotspot or a rearranged magnetic geometry. The object is small. The consequences are large. The scale shifts again. Seconds of rotation can encode information about matter at nuclear scales. Years of cooling can encode information about conductivity in dense layers. The path forward is not a leap. It is a slow tightening of constraints. Each observation adds a boundary. Each boundary narrows what the interior can be. The scene returns to the expanding debris. Filaments thin and stretch. Shadows deepen as light fades. The central sphere stays compact. Its outline remains firm. The overall picture settles into a calm statement. Neutron stars matter because they place ordinary physics under extraordinary pressure and still produce readable signals. The next step moves closer to the surface. Attention shifts to the crust and the sharp boundary where radiation escapes. The journey continues by following that edge into the layered structure beneath it. A neutron star looks simple from far away, yet the first layers hide a rich boundary. The outer crust forms a rigid skin where matter becomes a lattice, and electrons flow through it. At this distance, the object appears as a small dark disk against a thin, drifting mist. The rim is clean. The shadowed edge fades into space without a visible atmosphere. A gentle glow can cling to parts of the surface, not as flame, but as heat, escaping a hard shell. The scene slows near the surface. A hard boundary sits where gas ends and solid begins. In that narrow region, light behaves as though it departs from a curved shoreline. The scale shift is immediate. A surface only tens of kilometers across still shapes radiation that travels for centuries across interstellar darkness. The crust itself is thin compared with the star's radius. Yet it carries much of the surface story. It supports bumps. It supports fractures. It supports gradients in temperature that change the way the star is seen. A single number anchors the feeling of compactness. The surface gravity is about 100 billion times stronger than Earth's. That is like turning a gentle slope into a near-vertical cliff. With that pull, even a small height change becomes a major shift in pressure. The atmosphere cannot remain tall and puffy. It compresses into a film. The film is so thin that it behaves more like a boundary condition than a weather layer. A visual anchor settles in. A dark sphere sits in darkness. A faint frost-like sheen hugs it. The sheen is not ice. It is the idea of an atmosphere squeezed into a near-invisible sheet. Across the sphere, a subtle gradient appears. One region is slightly brighter. Another region is slightly dimmer. The change is smooth, like a slow dusk spreading over a rounded hill. A small payoff arrives. The crust is not a vague shell. It is a stack of zones where pressure rearranges matter into new patterns. In the upper crust, nuclei form an orderly lattice. Electrons roam between them more like a sea than like bound companions. This is called a Coulomb lattice, a crystal of nuclei held by electric forces. It resembles a salt crystal in structure, but the pressure is the sculptor. It matters because it sets the surface rigidity and the conductivity that spreads heat. The analogy that holds the section steady is pottery clay under a heavy press. When pressure rises, the clay grains lock into a tighter texture. When pressure falls, the texture relaxes. In the same way, increasing depth tightens spacing and changes how the crust carries stress. The journey moves downward. In the deeper crust, the lattice becomes more packed. Neutrons begin to seep out of nuclei. They do not stream freely like gas. They form a dense background between nuclear clusters. This seepage is not a dramatic event. It is a threshold that arrives when pressure makes it favourable for neutrons to exist outside nuclei. Another small payoff lands with it. The crust is both solid and permeated. It is a rigid framework with a hidden component that can slip in subtle ways. This dual nature helps explain sudden changes in rotation seen in some neutron stars. The surface feels like one piece. The interior coupling can lag, then it can catch up. The geometry of the boundary remains important. The crust is not perfectly smooth. Tiny mountains can exist, yet they are limited by the crushing gravity. A bump that seems large on a planet becomes impossible here. The physical detail that persists is curvature. Even a slight bulge changes the local slope of the surface. It changes how heat flows. It changes how emitted light is beamed and bent. In that region, light behaves as though it leaves a steep well. Paths curve, angles warp. A spot near the limb can remain visible longer than expected. A ring-like halo of weak emission can appear around the edge in certain conditions shaped by bending rather than by extra material. A new visual anchor appears around the one already held. The sphere is imagined with faint contour lines. The lines trace equal temperature. They gather closer near one pole. They spread wider near the equator. The pattern drifts slowly over time. The drift is not fast enough to feel like motion. It is slow enough to feel like cooling stone. The scale shifts again. Seconds of rotation can modulate that pattern. Yet the thermal map evolves over years as heat leaks outward through the crust. Here the limit of observation arrives gently and precisely. The crust's interior cannot be imaged directly. The surface is unresolved at typical distances. Even the best inference relies on light curves and spectra. Those signals fold together many effects. They mix temperature, magnetic geometry, and beaming. Different models can fit the same data. The uncertainty is not about whether the crust exists. The uncertainty is about exact composition and exact layering. It is about how impurities scatter electrons. It is about how cracks form under stress. It is about how heat channels along magnetic field lines that are not directly visible. Yet the crust still yields constraints. A signal would change if conductivity is high. A signal would soften if the surface has a thin atmosphere of light elements. A signal would sharpen if emission comes from a small hot region. Another payoff settles into place. The crust acts like a filter between the hidden interior and the escaping light. It shapes what leaves the star. It also shapes what can be learned from what leaves. The section ends by easing toward motion and rhythm. Once the crust and its boundary are set, rotation and magnetic structure begin to dominate the observed patterns. The next step follows repeating pulses and the geometry that makes a compact star act like a steady clock. Some neutron stars keep time with a steadiness that feels almost like a natural rhythm. That steadiness comes from rotation and a magnetic field that shapes where radiation escapes. At this distance, the star is a dark sphere with a faint rim of glow. Around it, space is not empty in a simple way. A structured region extends outward, where charged particles drift along invisible curves. The first clear image is a slow sweep. A narrow cone of emission passes across the darkness in a repeating pattern. It does not look like a beam in air. It looks like a moving slice of brightness on the edge of nothing. This is the core idea of a pulsar. A pulsar is a rotating neutron star that emits periodic beams. Like the rotating beam of a lighthouse, the sweep repeats with the same spacing. Like a sprinkler arm, the direction changes smoothly while the source remains fixed. This matters because repetition turns the star into a precise clock. The hook settles into a simple question. How can something so small create a signal that stays reliable for years? The early anchor answers it. Rotation supplies the rhythm and magnetism guides where the radiation is formed. The scene moves closer to the surface. A small hot region sits near a magnetic pole. The region is not a flame. It is an area where particles strike and heat the crust. The surrounding surface is cooler. A gradient forms between warmer and cooler zones. The border is smooth, not jagged. As the star turns, the warmer patch slides in and out of view. Light behaves as though it is leaving a curved well. Near the limb bending keeps the patch visible longer than expected. The result is a pulse that is not a sharp on and off switch. It is a rounded rise and fall. A small payoff arrives. The shape of a pulse can reveal geometry. A wider pulse hints at a broader emitting region. A narrower pulse hints at a tighter cone or a smaller hotspot. In that region, magnetism becomes more than a background feature. The magnetic field channels particles along arcs. It shapes a set of paths that resemble long loops stretching away from the star. It also sets the direction of the beam. The beam is not a spotlight in space. It is a pattern in the radiation produced by particles moving along field lines. The key physical detail is curvature. Field lines curve out from the surface and return forming a bundle. Where the bundle opens outward, particles can escape more easily. Where it closes, particles are trapped and redirected. This structure creates an emitting zone above the surface. It is thin compared with the star's radius, yet it controls the signal seen across great distance. A single number anchors the sense of speed. Some pulsars rotate about once each second. That is like a steady ticking metronome in an otherwise silent room. The scale shift is gentle. A 1-second rhythm at the star becomes a pattern that can be traced across thousands of years of travel time for the radiation. The journey passes a checkpoint. Rotation is not only speed, rotation is stability. A neutron star has enormous angular momentum for its size. Small changes in shape are resisted by the crust and by the tight packing of matter. This helps explain why the pulses can be so regular. Another visual anchor arrives. The star is imagined as a smooth black globe. 2 faint caps sit near the poles. Around the globe, a thin translucent halo forms a torus-like band of faint particle glow. The band is not a ring of solid matter. It is a region where particles circulate and radiate weakly. The band remains fixed in space while the star spins within it. The contrast between a stable outer structure and a spinning inner body feels calm. Another payoff settles into that calm. Pulsars can be measured by their timing alone. The star does not need to be bright overall. The pattern is enough. A signal would arrive as a repeating series of pulses. The exact arrival times can be compared over months and years. Tiny drifts reveal slow spin down. Those drifts encode energy loss and torque. The concept of spin down appears with a short definition, and then softens. Spin down is a gradual slowing of rotation over time. Like a top that slowly loses speed on a smooth floor, the period lengthens bit by bit. Like a swing that becomes less frequent as friction acts, the rhythm stretches. This matters because the rate of slowing hints at the magnetic field, strength and particle outflow. Here the limit of observation appears stated with care. The beam itself is not directly seen as a shape in space. Only the received pattern is known. Geometry must be inferred from a light curve that mixes many effects. The orientation of the rotation axis is unknown in most cases. The angle between magnetic and rotation axes is also uncertain. Models can fit the same pulse shape with different combinations of angles and emission heights. The limit is not a lack of data alone, it is a degeneracy in interpretation. Different arrangements can produce similar timing signatures. Even so, timing yields strong constraints. Another payoff lands. A very stable pulsar can function as a reference clock in the galaxy. If pulses arrive early or late by a small amount that shift, can signal changes in the path the radiation travels. Irregularities can reveal companions or intervening plasma. The signal becomes a probe of space itself, not only of the star. The scale shifts outward. The star is tiny. The pulses traverse a medium that is vast. Along the way, the radiation can scatter. Lower frequency waves smear more than higher frequency waves. The pulse can broaden as it passes through turbulent plasma. This adds another physical detail. A clean, sharp pulse can become a softened wave like light diffusing through frosted glass. That softening is not random noise. It carries information about the medium. The journey then returns inward. The source remains a rigid crust and a hidden interior. The pulse acts as the surface expression of deeper physics. The section eases toward the next step. Once rotation and magnetism create a pulsar, imperfections in that clock become especially revealing. The next section follows sudden changes in spin and what they suggest about internal coupling. A steady pulse becomes more informative when it briefly breaks its own rhythm. The most common reason is a glitch, a sudden small jump in spin that hints at hidden coupling inside the star. At this distance, the pulsar remains a faint point with a repeating pattern. The pattern is nearly uniform, then a slight shift appears in the spacing. It is not dramatic in brightness, it is a change in timing. The change feels like a quiet click in an otherwise smooth mechanism. The early anchor is simple. A glitch suggests that different layers inside the neutron star do not always rotate together. The scene moves inward from the beam to the body. A slow cutaway shows a rigid crust over a deeper region that is less rigid. The crust is imagined as a dark shell with fine hairline fractures. Below it, a paler layer moves without forming cracks. The boundary between them is not a sharp line. It is a zone with gradients in density and stiffness. Light behaves as a messenger only from the surface, yet the timing of that light can carry information from deeper down. A small payoff arrives. A glitch is not a burst of new energy. It is a transfer of angular momentum between internal components. The star does not suddenly push harder into space. Instead, one part hands rotational speed to another. The pulse shifts because the whole star's spin rate adjusts. The main concepts for the section settle into place. The first is the crust, a rigid lattice that can store stress. The second is superfluidity, a frictionless flow state in dense neutron matter. Superfluidity is flow without ordinary viscosity or drag. Like water that slips through a narrow channel without slowing motion, continues with very little internal friction. Like a smooth bearing that allows rotation with minimal resistance, a layer can keep a different pace. This matters because it allows the interior to lag behind the crust, and then catch up abruptly. The third concept is pinning, where vortices that carry rotation get stuck on imperfections. A vortex here is not a whirlpool in air. It is a microscopic thread of circulating superfluid. Many such threads form a hidden pattern like faint fibers aligned through a material. When the crust slows gradually, the superfluid can keep its earlier rotation. The difference grows quietly. Then the pinned vortices unstick in a cascade. Angular momentum moves into the crust. The crust speeds up a little. The pulse arrives earlier than expected. One number anchors the size of the event. A typical glitch can change the spin rate by about 1 part in a million. That is like a clock that suddenly gains about 1 second after 12 days. The scale shift is gentle. A microscopic unpinning event can lead to a measurable timing change across years of observation. A new visual anchor becomes the section's main scene. A dark sphere is wrapped in a thin shell that looks like cooled basalt. Beneath the shell, a clear layer holds a set of faint spiral threads. The threads slowly drift relative to the shell. Then a small region snaps into alignment. The shell relaxes. The threads redistribute. The external pulse pattern settles into a slightly faster beat. Another payoff follows immediately. The size and frequency of glitches can hint at how strongly the crust and the interior are coupled. Frequent small glitches suggest many small rearrangements. Rare large glitches suggest stress building over longer periods. In that region, the star behaves like a system with 2 clocks that usually agree. Most of the time, magnetic torque slowly slows the crust. The interior stays close but not perfectly. The mismatch is a reservoir. When release happens, timing reveals it. The journey passes another checkpoint. The crust is not just a passive shell. It can crack under stress. It can shift in plates that are small compared with a planet yet large relative to the star's surface features. A crack changes the local density profile. It changes the surface temperature map. It can change how particles return to the surface along magnetic field lines. Even then, the most stable signature is still timing. In that region, a signal would show a sudden step in rotational phase. Then it would show a recovery. The recovery can be slow, like a gradual easing back toward the previous trend. The ease is not an apology. It is the system settling into a new balance between layers. Here the limit of observation is clear and soft. The interior is not directly seen. Glitch models rely on inference from timing residuals. Different internal structures can mimic similar glitch patterns. The exact depth of the superfluid reservoir is uncertain. The distribution of pinning sites is also uncertain. Even the crust thickness is not directly measured. The limitation comes from resolution and degeneracy. Timing can tell that something changes. Timing alone cannot uniquely specify which layer changes without additional constraints. Yet the method still narrows possibilities. Another payoff arrives as a calm statement. Glitches prove that neutron stars are not perfectly rigid spheres. They are layered. They are dynamic. They store and release angular momentum in a way that reflects quantum behavior on a macroscopic scale. The scale shift is repeated in a softer way. Nuclear scale vortices far smaller than a grain of dust shape a global clock that is stable enough to be tracked for decades. The scene returns to the surface edge. The rim glow remains faint. The pulse continues. It carries the star's long-term spin down with occasional small interruptions. The next step moves from timing irregularities to the broader geometry that creates pulses in the first place. Attention shifts to the magnetic field structure and the regions where particles accelerate above the surface. A neutron star can seem quiet, yet the space around it can be shaped into a strict geometry. That geometry comes from a magnetic field that forces charged particles to follow curved paths. At this distance, the star is a dark sphere with a faintly lit cap. Above it, a delicate web of lines can be imagined. Those lines do not glow by themselves. They are a map of where motion is allowed. A slow scene forms as the main visual anchor. A thin veil of charged particles hangs over the surface. It gathers into 2 bright arcs near a pole. The arcs rise and fade like dim curtains. Between them a darker gap stays empty. The boundary of that gap is sharp. The contrast makes the field feel like a sculpted frame. The early anchor settles into plain language. Magnetism does not only add force, magnetism organizes where radiation forms and how it leaves. The section keeps 3 concepts. The first is the magnetic field, a structure that guides charged motion. The second is the magnetosphere, the region where the field dominates particle behavior. The third is the acceleration gap, a place where electric fields push particles to high energy. An acceleration gap is a region with strong electric fields along magnetic lines. Like a steep ramp that turns a slow slide into fast motion energy, increases over a short distance. Like a narrow chute that channels loose sand into a focused stream motion, becomes directed. This matters because it creates the radiation that later appears as pulses. The journey moves from the surface outward. Near the crust, the field lines curve tightly. They arch away from the surface. They return and close like loops. Farther out, some lines open and extend outward. In that region, particles can escape. The physical detail that anchors the idea is curvature and opening angle. A closed loop traps motion. An open line allows flow. This difference sets where a beam can form. A small payoff arrives. A pulsar beam is not a flashlight. It is a pattern created where particles accelerate and radiate along selected field paths. The scene shifts to the place where rotation matters. As the star spins, the field structure rotates with it. Yet there is a boundary in the magnetosphere where co-rotation becomes difficult to maintain. At that boundary, the field cannot force all plasma to keep up. Gaps can appear, electric fields can grow. The result is particle acceleration that feeds radiation. One number anchors the scale of the region. The light cylinder radius for a 1-second pulsar is about 50,000 kilometers. That is like the distance across a continent. The scale shift is gentle. A star only tens of kilometers wide influences a magnetic structure that reaches tens of thousands of kilometers outward. The inner and outer scales remain connected by rotation. Another visual anchor arrives within the main scene, kept slow and concrete. A faint cylindrical surface is imagined around the star. It is not a material wall. It is a geometric boundary. Inside it, field lines sweep smoothly. Near it, they stretch and twist. The twisting creates a spiral pattern in the outflow. The spiral is subtle, like smoke lines that curl from a quiet incense stick. The pattern stays stable for many turns. Another payoff settles. The shape of the magnetosphere can set the pulse profile even when the surface is not changing. Small shifts in the gap location can alter the beam. Small changes in plasma density can widen or narrow the emitting region. These changes can be tracked through timing and spectrum. The checkpoint cadence moves outward again. Beyond the inner region, particles can stream along open lines. Their motion produces radiation that can spread across a broad range of energies. The exact mechanism can vary. Curvature radiation appears when particles follow curved paths and radiate. Curvature radiation is emission from charges forced along curved trajectories. Like a car that emits a spray of gravel when turning hard, energy sheds when the path bends. Like a garden hose that releases mist when the stream is forced around a tight curve, the direction change produces a pattern. This matters because it ties the beam to field line shape. The physical detail returns to the arcs near the pole. The arcs shimmer faintly. The gap between them stays darker. The edge of the emission region remains crisp. The border can drift a little as plasma conditions change. That drift can change pulse width. It can change pulse symmetry. Another payoff arrives with a quiet precision. A broader pulse suggests a wider range of magnetic longitudes contributing emission. A sharper pulse suggests a more confined gap. The geometry becomes a ruler. Here the limit of observation arrives softly and clearly. The magnetosphere cannot be imaged directly at typical distances. Only the emitted radiation is received. That radiation is filtered by propagation through plasma and by relativistic beaming. Different magnetosphere models can reproduce similar pulse shapes. The same pulse shape can come from different combinations of viewing angle and emission altitude. The limitation is a degeneracy between geometry and physics. Indirect inference is powerful yet not unique. Even so, some constraints remain robust. The presence of high-energy emission implies strong acceleration. The stability of the pulse implies a stable large-scale field. The occasional drift implies changing plasma supply. The scale shift returns in a calm way. A microscopic supply of charges at the surface can alter a magnetosphere that spans continents in radius. A slight change in surface temperature can change emission of particles. That change can ripple outward into the gap region. The scene eases back toward the star's rim. The faint cap remains. The arcs fade and return. The emission pattern stays steady enough to be recognizable. The next step moves toward stronger fields and more dramatic magnetic dominance. Attention shifts to magnetars, where field strength can reshape the crust and alter radiation in brief episodes. Some neutron stars feel defined by timing, yet some feel defined by the force of their magnetic environment. A magnetar is a neutron star whose magnetic field dominates its behavior and its signals. At this distance, the object is still a small dark sphere. Around it, the surrounding region looks tense and structured. A faint haze takes on a braided appearance. The brightness does not sit evenly. It gathers into thin bands that curve and reconnect. The early anchor is calm and direct. A magnetar stands out because its magnetic field stores energy that can be released through the crust and the magnetosphere. The scene begins with the section's main visual anchor. The surface is imagined as a dark shell with a network of pale fracture lines. Some lines are old and faint, some are fresh and bright. Near one pole, a crescent-shaped hot region glows softly. Above that region, a loop of magnetic field arches outward and returns. The loop is thick with faint particle glow. The edges of the loop are sharper than the surrounding haze. The boundary looks like a drawn curve in smoke. A subtle shadow forms beneath it where emission is weaker. This scene stays slow. It does not flare like a storm. It holds tension like a stretched cord. The section keeps three concepts. The first is magnetic stress, the force the field exerts on the crust. The second is the crust fracture, a mechanical release when stress exceeds strength. The third is twist, a change in field geometry that drives currents. A twist is a shear in magnetic field lines that stores extra energy. Like a twisted rubber band that keeps energy in its shape, the field holds tension without moving mass far. Like a coiled spring that tightens without changing its length, much geometry becomes storage. This matters because a change in twist can change how particles accelerate and how radiation appears. A small payoff arrives. Magnetar activity can be understood as geometry and stress, not as simple heating alone. The journey moves inward first. The crust is rigid but not unbreakable. Stress builds slowly as the internal field evolves and shifts. The crust resists. Tiny fractures can form and stop. Stress can migrate. When a larger fracture occurs, the surface pattern changes. A hotspot can brighten. A pulse can change shape. The physical detail is the fracture network and the thermal gradient around it. Heat spreads outward from a crack zone. The gradient forms a smooth halo with a brighter center and a dimmer rim. The rim looks like a soft ring around a crescent. Light behaves as though it leaves from that hot region and bends along the curved edge of the star. A second payoff settles. A magnetar can change its radiative pattern without changing its rotation much. The clock remains, the beam changes, the magnetosphere becomes the next checkpoint. Above the surface, twisted field lines carry currents. Those currents supply charged particles. Particles scatter photons. The scattering reshapes the spectrum and the pulse profile. Here a term appears briefly and is released. Resonant scattering is photon scattering enhanced by magnetic conditions. Like mist that thickens into visible fog near a cold boundary, scattering becomes efficient in a narrow region. Like sunlight that turns pearly when it passes through thin cloud, layers the same light emerges changed. This matters because it turns surface heat into a different observable signal. One number anchors the scale of magnetic strength in a safe way. A magnetar field can reach about 100 trillion Gauss. That is like turning a mild compass influence into a force that rules the entire surrounding region. The scale shift is gentle. A field anchored in a crust only tens of kilometers across can control particle motion far beyond the star. The main visual anchor deepens rather than changes. The loop above the hot crescent becomes slightly brighter along its inner edge. The outer edge stays dim. The loop's thickness varies like a rope seen in low light. The emission is not uniform. It has a gradient. The brightest region sits where the loop foot points touch the crust. The dimmest region sits near the apex. The loop looks stable, yet it is not a rigid object. It is a region where particles move and radiate. Another payoff arrives. When the magnetosphere twists and untwists, it can change the opacity of that region. A pulse can become sharper or smoother without any need for a new hotspot. The line between surface physics and magnetospheric physics becomes blurred in a useful way. The next checkpoint is release. Magnetars sometimes show short bursts of radiation. Those bursts can be linked to sudden reconfiguration of the magnetic field and crust. The section keeps calm by describing aftermath rather than spectacle. After a release, the hot region can cool. The loop can relax into a less twisted shape. The fracture lines can fade. The emission can settle into a quieter pattern. The rhythm returns. The object remains compact. The surrounding haze remains structured. Here the limit of observation appears with precision. The crust fracture and field twist cannot be watched directly. Only the emitted radiation is received. Even that radiation is filtered by scattering in the magnetosphere. Different combinations of hotspot size, twist angle, and scattering depth can produce similar pulse shapes and spectra. The limitation is a degeneracy in modelling. The surface map is not resolved. The magnetosphere is not imaged. The inference must be indirect and statistical. Yet the process still constrains. Slow changes in pulse profile can track untwisting. Cooling curves can constrain heat capacity in the crust. Burst energies can constrain the stored magnetic stress. Another payoff arrives as a quiet synthesis. Magnetars show that magnetic energy can be a primary reservoir, not just a guide. That reservoir couples to a rigid crust and a dynamic magnetosphere. The scale shift returns in a soothing way. A microscopic rearrangement of currents along field lines can alter emission across a region larger than continents. A crack pattern across kilometers on the surface can affect signals that cross the galaxy. The scene returns to the dark sphere. The crescent glow softens. The loop remains as a faint arc. The fracture network becomes less distinct. The next step moves from these strong magnetic environments back to signals as messengers. Attention shifts to how different kinds of radiation carry different information from the same compact source. A neutron star speaks in more than one kind of light, yet each kind carries a different kind of truth. The differences come from where the radiation forms and what the surrounding space does to it. At this distance, the star is a small dark disk with a faint glow near one edge. Around it, the magnetosphere looks like a thin, uneven fog. It is not uniform. It has layers. It has gaps. It has curved bands that drift and reconnect. The early anchor settles into plain language. Radio waves often trace geometry and plasma, while higher energy light often traces hotspots and strong scattering. The section keeps three concepts. The first is emission region, the place where radiation originates. The second is dispersion, the spreading of a pulse by plasma along the path. The third is scattering, the reshaping of light by interactions near the star. Dispersion is a delay that depends on wave frequency. Like a long hallway where low notes echo longer than high notes' arrival times separate. Like a slow tide that pulls heavier debris later than lighter foam, the same event stretches out. This matters because a pulse can reveal the density of plasma along the line of travel. The main visual anchor forms as a calm composite scene. A single pulse leaves the star as a sharp event. Far away it arrives as two versions of itself. One arrives crisp and narrow. The other arrives softened and delayed. The crisp one is imagined as a thin, bright line in darkness. The softened one is imagined as a broader smear. The smear has a rounded leading edge. It has a trailing tail that fades slowly. The tail is not noise. It is a signature of the medium. The physical detail that holds the image is that tail and its gradient. The tail falls off smoothly. It looks like a brushstroke thinning at the end. A small payoff arrives. A pulse that is smeared has not lost information entirely. The amount of smearing can be measured and used as a probe of space between source and receiver. The journey moves through checkpoints. First is the surface and near-surface region. Thermal emission comes from the crust in any hotspots. It is often smoother in time. It can still be modulated by rotation, but its spectrum carries temperature. A hotspot has a gradient from center to rim. The center is brighter. The rim is dimmer. The border is soft. That softness is a clue. Light behaves as though it leaves from a curved surface and is bent. A hotspot near the limb can remain visible longer due to bending. This can make a pulse appear wider in higher energy light. A second payoff settles. Pulse width is not only a beam property, it can be a geometry and gravity property. The next checkpoint is the radio-emitting region. It often sits higher in the magnetosphere than the thermal surface emission. It can form along open field lines where particles move outward. The radio beam can be narrower or wider depending on the altitude and plasma conditions. In that region, plasma density changes with height. The gradient can be steep. This affects dispersion and scattering. A pulse that is sharp at the source can be stretched by dispersion as it travels through ionized gas. Another visual anchor appears within the main scene, kept slow and distinct. A thin ribbon of radio emission travels through a faint cloud. The cloud is not solid. It has clumps. Each clump adds a tiny delay. The ribbon emerges with its front edge rounded. The back edge trails. The trail looks like a fading wake. Another payoff arrives. The frequency dependence of that delay can separate the effects of path length from the effects of plasma. The journey then returns closer to the star for higher energy processes. In strong magnetic fields, particles can scatter photons in preferred directions. Scattering does not simply blur, it can redirect. It can harden or soften the spectrum. It can move photons from one energy to another. The physical detail is an angular pattern. Some directions brighten, some directions dim. The result can be a pulse shape that changes with energy band. A pulse in lower energy light can look smooth. A pulse in higher energy light can look more peaked or more complex. Another payoff settles into that difference. Comparing pulse shapes across energies can separate surface hotspots from magnetospheric scattering. One number anchors the timescale for travel. A pulse can take about 1,000 years to cross 1,000 light years. That is like a message drifting across centuries yet keeping its rhythm. The scale shift is gentle. A millisecond scale feature at the source can arrive after centuries and still be recognizable, yet the medium can reshape it. The section pauses for a limit of observation stated clearly. No direct picture shows where each photon is created. The emission regions are inferred from timing spectrum and polarization. Even those can be ambiguous. Different altitude and geometry combinations can mimic similar pulse profiles. Dispersion and scattering along the path add further uncertainty. The limitation is a blend of resolution and model degeneracy. A pulse can be measured with great precision. The interpretation of its origin can still be non-unique. Yet constraints accumulate. If dispersion is strong, plasma along the path is dense. If scattering tails along turbulence is high. If high-energy pulses align with hotspot phases, surface emission dominates. Another payoff arrives. The multiband view turns one object into several probes. Radio traces the intervening medium and the magnetospheric flow. Thermal light traces crust temperature and hotspot size. Higher energy light traces acceleration and scattering. The scene returns to the composite pulse image. The thin line and the broad smear sit together. The smear is not a mistake, it is a record of travel. The thin line is not pure, it is a filtered reminder of origin. The next step eases toward the most extreme case of scattering and field dominance. Attention shifts to how Magnetar environments reshape spectra and timing, and how those changes can be tracked without needing a direct image. Deep inside the crust, matter changes shape in a way that sounds abstract, yet it leaves a practical imprint on behavior. The change is called nuclear pasta, a set of dense structures that form when forces compete at extreme pressure. At this distance, the neutron star remains a dark sphere. The surface glow is faint. The interior is imagined through a quiet cutaway. A shell of crust surrounds a deeper region, where density gradients steepen. The boundary between zones is not a line. It is a thickness where properties slide from one regime to another. The early anchor is simple. Nuclear pasta matters because it changes how the crust stores stress and how heat and particles move through it. The section holds three concepts. The first is nuclear pasta itself. The second is shear strength, the resistance to deformation. The third is thermal conductivity, the ease of heat flow. Nuclear pasta is dense nuclear matter, arranged into sheets and tubes. Like layers of lasagna pressed flat in a pan, matter forms stacked sheets. Like a bundle of drinking straws fused together, matter forms tubes and channels. This matters because those shapes change how the crust responds to strain and how it transports heat. The main visual anchor is a slow interior landscape. A dim cross-section shows a band where matter is not granular. It looks like folded ribbons. Some ribbons run parallel for a while. Some merge and split. Between them, narrow voids form channels filled with a dense background. The edges of the ribbons are smooth. The spacing between them varies gradually like ripples on a calm dune. The scene stays steady. It feels more like geology than like turbulence. A small payoff arrives. The crust is not only a crystal of nuclei. In the pasta layer, the geometry becomes complex enough to behave like a different material. The journey moves through checkpoints from shallow to deep. In the upper crust, nuclei sit in a lattice and electrons flow around them. In the deeper crust, neutrons begin to appear outside nuclei. Then pressure rises further. The attractive nuclear force pulls matter together at short range. Electric repulsion pushes charged parts apart at longer range. Where these forces balance, matter chooses shapes that reduce energy. The result is not a random mess. It is a set of repeating motifs. Sheets, rods, and junctions appear. Each motif has a different stiffness and a different pattern of scattering for moving particles. The physical detail that anchors this is layering. The pasta region is not the entire star. It is a band. It sits like a stratum in sediment. Above it, the lattice is more regular. Below it, matter becomes closer to a uniform fluid. The scale shift is gentle. Structures that are microscopic in thickness can influence a crust that spans kilometers. Those kilometers then influence a star that stays only tens of kilometers across. One number anchors the depth in a safe way. The pasta layer can span about 1 kilometer in thickness. That is like the height of a mountain compressed into a shell inside a small sphere. The comparison helps hold the idea. A mountain height becomes an interior band. That band changes the star's response to stress. Another visual anchor appears within the main scene kept distinct. A slow wave of heat moves through the cutaway. In the crystalline layer, the wave spreads smoothly. In the pasta band, the wave spreads unevenly. It follows channels. It slows across sheets. The heat front bends like water flowing around a line of submerged stones. Another payoff arrives. Thermal conductivity is not uniform. The pasta geometry can make heat flow easier in one direction than another. This can help create lasting temperature patterns on the surface. Those patterns can shape pulses. The journey moves to stress and motion. The crust stores strain from magnetic forces and from spin changes. When strain builds, the crust can crack or shift. The pasta layer may act like a buffer. It may absorb strain differently than the crystalline regions. It can also affect the coupling between the crust and deeper components. A small payoff settles. If the pasta layer is strong, it can support larger elastic deformations. If it is weaker, it may allow slippage that changes how glitches unfold. The section remains calm by staying with gradual effects. No dramatic rupture is required. Small differences in material properties can change long-term timing behavior. They can also change cooling curves after heating events. Here the limit of observation appears with clarity. The pasta layer cannot be seen directly. No signal carries an image of those sheets and tubes. Evidence comes from models that connect microphysics to measurable behaviour. Cooling rates, glitch recovery and oscillation frequencies can all be influenced by the pasta layer, yet each observable is shaped by several factors at once. Different interior assumptions can reproduce similar surface signals. The limitation is a degeneracy of inference. The resolution is not spatial. The resolution is parameter space narrowed slowly by multiple kinds of data. Another payoff arrives. Even without direct access, the existence of a transition band is strongly motivated by known forces and by the need to reduce energy at high density. The precise geometry may vary. The presence of a complex layer remains plausible and useful. The scale shift returns in a soothing way. Nuclear forces act across distances far smaller than a cell, yet their balance can create kilometre-thick layers. Those layers can shape a star's long-term behaviour across thousands of years of cooling and torque. The main visual anchor returns to the folded ribbons. They remain steady. The channels between them remain dark and narrow. The heat wave slows and spreads. The next step moves deeper beyond the crust's last structured band. Attention shifts toward the core and the uncertainty of what matter becomes when even nuclear pasta is left behind. The deepest parts of a neutron star are never directly seen, yet the outer signals still carry hints of what lies below. The reason is simple. The core sets the star's size and stiffness which shape everything else. At this distance, the star is a small dark sphere with a steady pulse. The surface remains the only visible boundary. Beneath that boundary, density rises quickly. The rise is not a sudden step. It is a steep gradient that smooths from crust into core. A calm cutaway forms and stays as the main visual anchor. The outer shell appears as a thin, darker rind. Below it, the interior shifts into a uniform-looking region, like a deep ocean that loses all landmarks with depth. The brightness in the cutaway is not light. It is a way to show pressure. It deepens smoothly toward the centre. The early anchor settles into plain language. The core matters because different core states predict different sizes, cooling rates, and responses to stress. The section holds three concepts. The first is the equation of state, the relation between pressure and density. The second is phase transition, a change in the state of matter at high density. The third is compressibility, how easily matter squeezes under pressure. An equation of state is the rule linking pressure to density. Like a recipe that fixes how batter thickens as flour is added, it sets how stiffness grows as density rises. Like a map that relates depth to water pressure, it tells how conditions change inward. This matters because it predicts the star's radius for a given mass. The journey moves inward by checkpoints. The crust ends when nuclei dissolve into a more uniform mixture. Past that, the core begins. In the outer core, neutrons and a smaller fraction of protons and electrons can exist in a dense fluid. The fluid is not like water. It is a strongly interacting quantum system. The physical detail that anchors it is stratification by density. Small changes in radius correspond to large changes in pressure. The interior is layered by gradients rather than by hard boundaries. In that region, motion would be guided by buoyancy and by composition differences. Even slow rotation can create subtle equatorial bulges. Those bulges reflect stiffness. A small payoff arrives. A stiffer core resists compression. It produces a larger radius and a stronger resistance to deformation. A softer core compresses more. It produces a smaller radius and allows larger changes under the same stress. One number anchors the scale without becoming fragile. The central density can reach several times the density of atomic nuclei. That is like compressing a familiar solid until its interior is packed beyond the point where separate atoms remain meaningful. The comparison is not meant to be exact. It is meant to keep the scale safe and grounded. The scale shift is gentle. Changes at nuclear scales influence a star wide enough to span a city. Those same changes influence signals that travel across the galaxy. The journey approaches the uncertain frontier. At higher densities, matter may change phase. It may form exotic particle populations. It may form a different arrangement of quarks. The section stays calm by limiting the list. Only the idea of change is needed, not every candidate. A phase transition is a change in matter state under new conditions. Like water that becomes ice when temperature crosses a threshold, structure changes when pressure crosses a threshold. Like wax that shifts from solid to soft when warmed behavior can change without changing composition much. This matters because it can soften or stiffen the equation of state in a narrow density band. The main visual anchor deepens. In the cutaway, a faint boundary appears as a subtle ring. It is not a sharp line. It is a zone where the shading changes slightly faster with depth. The ring suggests a transition region. Outside it, the gradient is smooth. Inside it, the gradient steepens or relaxes. This is how a phase transition might appear in a schematic sense. Another payoff arrives. If a transition softens the core, the star may become more compressible. That can reduce radius. It can also influence the maximum mass a neutron star can support before collapsing further. Without using dramatic language, this becomes a quiet filter. Observed masses and radii can rule out some equations of state. The journey then returns to what can actually be inferred. Signals do not carry a direct sample of core matter. They carry integrated consequences. Cooling curves depend on which neutrino processes operate. Rotational behavior depends on internal coupling and viscosity-like effects. Oscillation frequencies depend on stiffness and stratification. Each is a partial window. Another visual anchor appears within the main scene, kept slow and distinct. A ripple travels through the cutaway like a gentle wave in a thick fluid. The ripple changes speed as it crosses layers. In stiffer regions, it moves faster. In softer regions, it slows. The ripple fades. The surface pulse remains steady. Another payoff settles. Starquakes, glitches, and pulse timing can act like distant seismology, even when the waves themselves are not directly detected. Here, the limit of observation is stated with care. The core cannot be resolved in space. It cannot be sampled in material form. Models must map from interior physics to exterior signals. That mapping is many to one. Different microphysics can produce similar macroscopic properties. Measurement uncertainties add further blur. Radius estimates can depend on atmosphere assumptions. Cooling interpretations can depend on unknown heating histories and magnetic channeling. The limitation is not a lack of imagination. It is a lack of unique inversion. Even so, constraints improve when multiple observables are combined. Another payoff arrives. A reliable mass measurement can eliminate very soft equations of state. A radius estimate can narrow stiffness. A cooling trend can hint at whether fast neutrino emission operates. Together they carve away possibilities. The scale shift returns in a soothing way. A slight change in particle interactions invisible at any distance can alter the star's size by kilometers. Those kilometers can alter pulse shapes through light bending and hotspot visibility. The main visual anchor returns to the deep cutaway. The subtle transition ring remains faint. The center stays featureless like a calm abyss that refuses direct description. The section ends by easing toward a more direct kind of constraint. When neutron stars orbit companions, gravity and motion can reveal mass and radius-related properties, with less dependence on surface emission details. The next step moves outward into binary dynamics, and the way orbits become another signal. A neutron star becomes easier to weigh and constrain when it shares its gravity with a companion. The orbit turns invisible mass into a repeating pattern that can be timed and modelled. At this distance, two compact objects trace a silent dance in darkness. No trail marks their paths. Only the geometry of their motion matters. The early anchor is calm and direct. Orbital timing and relativistic effects can constrain mass and sometimes radius-related properties with fewer assumptions about surface emission. The section holds three concepts. The first is binary orbit, the repeated motion of two bodies around a center. The second is tidal interaction, the stretching caused by differential gravity. The third is relativistic time delay, small timing shifts caused by curved space-time and motion. A relativistic time delay is a timing shift caused by gravity and motion, like a long walk through soft sand that takes longer than the same distance on firm ground. Signals arrive later in deeper gravitational wells. Like a winding row that adds time compared with a straight path curved space-time, adds delay along the route. This matters because timing changes can reveal mass even when the bodies remain unresolved. The main visual anchor forms as a slow orbital scene. Two dark spheres circle a shared point. Their motion is smooth. The orbit is slightly elongated, like an oval traced in faint dust. At two opposite points, the spheres move faster. At the wider ends, they move more slowly. Around the pair, a thin, dim band of gas forms a faint arc. The arc is not a thick disk. It is a sparse veil that hints at the environment. The key physical detail is the changing separation and the changing speed. The near pass is tight. The far pass is wide. The rhythm of near and far repeats. A small payoff arrives. The orbit itself becomes a clock. Once the orbital period is known, shifts in that period reveal energy loss and gravitational effects. The journey moves through checkpoints of what the orbit can reveal. First is mass from Keplerian motion. The path and period link to total mass. In a pulsar binary, the pulse train adds precision. Each pulse is a marker. The orbit shifts the arrival times by a repeating pattern. When the pulsar is on the far side, pulses take longer to reach distant space. When it is closer, pulses arrive sooner. Light behaves as a messenger that is delayed by changing path length and by gravity. Another payoff settles. Even without any image, a timing curve can map the orbit's size and orientation. The next checkpoint is relativistic precession. The orbit can rotate slowly in space. The point of closest approach can advance. This is not a wobble in brightness. It is a geometric drift of the ellipse itself. The physical detail is a slow turning of the oval path like a leaf orbit that gradually rotates while keeping its shape. The effect is small but cumulative. Over years it becomes measurable in timing residuals. Another payoff arrives. The rate of this advance depends on mass and separation. It can provide a strong mass constraint without needing thermal modelling of the surface. The next checkpoint is time delay from curved spacetime near a companion. When the pulsar passes behind its companion from the line of sight, pulses can be delayed by an extra path through curved spacetime. The delay is like a soft pause. It is not a blackout. It is a slight shift in arrival time. A visual anchor appears within the main scene, kept slow and distinct. The pulse train is imagined as a string of evenly spaced points moving along an invisible line. Near the companion, the spacing stretches slightly. Then it returns to normal. Another payoff arrives. This delay can constrain the companion's mass and the inclination of the orbit. The journey then moves toward tides, which add sensitivity to radius. Tidal interaction is the differential pull that stretches a body. In a close binary, each object can raise a bulge on the other. A tidal bulge is a deformation caused by uneven gravity. Like a water droplet that elongates when pulled from two sides, shape changes under differential force. Like bread dough that stretches into an oval, under gentle tension the body becomes slightly less spherical. This matters because the ease of deformation depends on internal stiffness and radius. One number anchors the orbital scale in a safe way. Some compact binaries complete an orbit in about a few hours. That is like the cycle of a quiet tide in a small bay repeating through a single night. The scale shift is gentle. A few-hour rhythm can continue for millions of years while slowly evolving. The orbit is both fast and ancient. The main visual anchor deepens. At closest approach, faint bulges appear on the facing sides of the spheres. The bulges are subtle. Their edges are smooth. The spheres remain nearly round. The bulges shift as the orbit progresses. They grow slightly near the close pass. They relax slightly near the far pass. Another payoff arrives. Measuring how easily a neutron star deforms under tides can constrain its equation of state. A stiffer star deforms less, a softer star deforms more. This connects core physics to orbital signals without needing to see the core. Here the limit of observation appears with clarity. The orbit can be timed with high precision in favourable cases. Yet the interpretation can still be limited by unknown companion properties and by distance-related uncertainties. Tidal signatures can be subtle. They can be entangled with spin effects and with the details of the system's formation. In some systems, only total mass is well constrained. In others, inclination remains uncertain. The limitation is not a missing concept. It is that many parameters can trade off in models. Even so, certain combinations are robust. A large relativistic advance implies high mass or tight separation. A strong time delay implies a specific orientation. A consistent orbital decay implies energy loss through gravitational radiation. Another payoff arrives. Binary systems act like natural experiments with repeated trials. Each orbit repeats. Each repeat refines constraints. Over years, the accumulation of timing data narrows the allowed mass range. The scale shift returns softly. A compact orbit only a few light seconds across can teach about matter at nuclear densities. That teaching comes from repeated timing patterns rather than from direct images. The scene eases outward. The two dark spheres keep circling. The faint arc of surrounding gas remains thin. The next step moves toward the end states of the closest binaries. Attention shifts to inspiral and merger, where orbital energy loss becomes rapid and new signals emerge. An orbit that slowly shrinks can stay calm for a long time, yet it quietly carries the seeds of a final convergence. The reason is energy loss through gravitational radiation, which draws two neutron stars closer until separation becomes small. At this distance, the pair is seen as two dark spheres circling in a thin, cold emptiness. Their path is a smooth oval. The oval tightens almost imperceptibly from one cycle to the next. The early anchor is clear. Inspiral and merger turn orbital motion into signals that can constrain neutron star stiffness through tides and dynamics. The section holds three concepts. The first is gravitational radiation energy carried away by ripples in space-time. The second is Chirp, a rising frequency pattern as the orbit accelerates. The third is tidal deformability, how easily a star's shape changes under a companion's pull. A chirp is a signal that rises in frequency as time passes, like a slow drum beat that gradually becomes quicker. Spacing between beats shortens. Like footsteps that come closer together as a walk becomes a run, the rhythm tightens. This matters because the pattern is directly tied to mass and separation. The main visual anchor forms as a slow tightening spiral. The two spheres circle each other. Each loop is slightly smaller than the last. A faint trace of their path is imagined as a thin line like chalk on dark stone. The line coils inward. Near the centre, the coils become closer together. The speed increases. The distance between the spheres decreases. The physical detail that anchors the scene is the changing curvature of the orbit. The path bends more sharply as separation shrinks. Another detail appears as tides. Each sphere develops a subtle bulge on the facing side. The bulge is smooth. Its edge is a gradient rather than a ridge. The gradient becomes slightly steeper as the spheres approach. A small payoff arrives. Tides are not only a shape detail. They alter the orbit by stealing energy and by changing the gravitational field pattern. The journey moves through checkpoints. First is the long inspiral. The orbit remains wide compared with the stars. The change per orbit is tiny. Over millions of years it accumulates. The scale shift is gentle. A final second of rapid motion sits at the end of a history longer than recorded civilization. The next checkpoint is the late inspiral, when the orbital period shortens and the star's internal stiffness becomes important. A stiffer star resists deformation. A softer star yields more. Yielding changes the gravitational radiation pattern slightly. That slight change integrated over many cycles can become measurable. One number anchors the late-stage timescale. The final few seconds can contain much of the most informative evolution. That is like the last few notes of a long musical phrase where the theme resolves and becomes clear. The comparison keeps the intensity low while keeping meaning. The main visual anchor deepens, the spiral path tightens. The chalk-like trace becomes brighter near the centre, not from light but from attention. The bulges on the spheres become a little more pronounced. The facing surfaces flatten slightly where gravity pulls hardest. A thin, dark gap remains between them until the end. The gap narrows. Another payoff settles. The moment of closest approach is not only a collision. It is a probe of how matter responds when pushed to extreme density and rapid motion. The journey then crosses the threshold into merger without spectacle. The two shapes touch. The boundary between them blurs. The combined mass forms a single, rapidly rotating object for a brief time in some cases. In other cases, collapse to a black hole can follow quickly. The section stays calm by focusing on structure rather than drama. The merged object can have a hot outer layer and a denser inner core. The outer region can form a thick torus of debris. The torus is not a neat ring, it is a swirling uneven band with gradients in density. Its inner edge is sharp, its outer edge fades into a diffuse tail. The physical detail is that edge and the shear flow along it. Layers slide past each other, friction-like processes heat the gas. Another payoff arrives. The post-merger structure depends on stiffness. A stiffer equation of state can support a larger remnant temporarily. A softer one leads to quicker collapse. The gravitational radiation pattern changes accordingly. Here the limit of observation is stated clearly. The merger is brief. The highest frequency part of the signal is hardest to capture cleanly. Noise and limited sensitivity can obscure fine features. Even when a chirp is detected, separating tidal effects from mass ratio and spin can be challenging. The limitation is not only distance, it is also model complexity and parameter degeneracy. Different combinations can create similar chirps. Yet the in-spiral phase provides strong constraints. The mass scale is often well measured. Tidal deformability can be bounded even when not precisely measured. Another payoff settles. A single in-spiral detection can rule out extremely soft or extremely stiff models. Multiple detections can map a range. The scale shift returns softly. Nuclear scale stiffness influences kilometer scale deformability. That deformability influences a signal that travels for millions of years through intergalactic space. The main visual anchor returns to the tightening spiral. The last loops are close together. The spheres are nearly touching. The scene then eases outward again. The merger is not held as a cliff. It is treated as a bridge. The next step moves from the immediate event to the longer aftermath. Attention shifts to how remnants cool, settle, and seed surrounding space with heavy elements without needing a view of the core itself. After a merger, the most important changes are not loud in appearance but slow in structure and heat. The remnant settles by shedding energy through radiation and by rearranging matter under gravity. At this distance, the scene is a dark region with a single compact center. Around it, a thick band of debris turns in a wide arc. The band is uneven. Its inner edge is sharper than its outer edge. The early anchor is simple. The aftermath links neutron star physics to long-term cooling ejected matter and lasting signals that persist after the main event. The section holds three concepts. The first is Remnant, the compact object formed immediately after merger. The second is Ejecta, the material thrown outward. The third is opacity, the property that controls how easily light escapes from that material. Opacity is how strongly matter blocks and scatters radiation. Like fog that turns a distant lamp into a soft smear, high opacity spreads and dims light. Like thick curtains that let only a faint glow through fabric, high opacity traps light longer. This matters because opacity sets how bright and how long post-merger glow can last. The main visual anchor forms as a slow expanding veil. A crescent of material peels away from the merger site. It does not explode like a flash. It expands like a slow breath. The leading edge is thin. It is a curved front with a smooth gradient from dense to diffuse. Behind it, the debris band remains. The band turns like a broad river around a drain. Its surface has ripples and darker lanes. Those lanes mark shear. The physical detail that holds the image is the contrast between the sharp inner edge and the fading outer tail. The tail feathers into darkness. A small payoff arrives. Ejecta does not need to be a large fraction of mass to matter. Even a thin veil can dominate the visible glow if its opacity traps heat and delays release. The journey moves through checkpoints of time. Immediately after merger, the remnant is hot. It can be supported by rapid rotation and pressure. Over time, it cools and loses rotational energy. The debris band can feed back onto the remnant through accretion, yet the section remains calm by focusing on gradual flows. The debris band is not a rigid ring. It is a thick torus with gradients in density. Its inner rim is compressed. Its outer rim is looser. Material slides along different speeds, creating shear layers that heat the gas. Another visual anchor appears within the main scene, kept distinct. Along the inner rim, a thin, bright line appears, a warm boundary where friction-like processes are strongest. The line is not a sharp beam. It is a narrow, glowing seam with a soft halo. Another payoff settles. The location of heating can be traced through how the glow changes over time and across energy bands. The next checkpoint is composition and opacity in the expanding veil. Ejecta can be rich in heavy elements formed through rapid neutron capture. Heavy elements have many bound electron transitions. That complexity increases opacity, especially in certain wavelengths. The glow becomes redder and longer lasting when opacity is high. This is a quiet consequence of atomic structure carried into astronomy. One number anchors the expansion scale safely. The ejecta can move outward at about 1/3 the speed of light. That is like a storm front crossing a continent in a few heartbeats, yet in space it remains a gentle, silent drift. The scale shift is calm. The expansion is fast by human intuition, but it plays out as a smooth change across days and weeks in the glow pattern. The main visual anchor deepens. The expanding veil thickens near the equator and thins near the poles. The thickness difference creates a soft asymmetry. In some directions, the glow is more blocked. In other directions, it escapes earlier. The boundary is not a hard edge. Boundary is not a hard. It is a gradient in optical depth. Another payoff arrives. Geometry affects what is inferred. A brighter early glow can mean lower opacity along that direction, not necessarily more energy. The journey returns to the remnant itself. If the remnant remains a neutron star for a while, it can radiate and drive winds. Those winds can add further material to the outflow. If collapse occurs quickly, the remnant becomes more compact and the central engine changes. The section stays neutral. Both paths are possible depending on mass and stiffness. In that region, a signal would show different durations and different spectral evolutions. Another payoff settles. The duration of sustained energy input after merger can hint at whether a massive neutron star persists temporarily. A persistent remnant can keep the surrounding material warmer for longer. A rapid collapse can shorten that input. Here the limit of observation appears clearly. Post-merger light is shaped by opacity, geometry, and thermalization efficiency. These are difficult to untangle without multiple wavelengths and good distance estimates. The ejecta mass and composition can trade off against viewing angle. The remnant lifetime can trade off against how efficiently energy couples to the outflow. The limitation is modeled degeneracy combined with incomplete coverage. Even so, certain features remain robust. A redder, longer-lasting glow suggests higher opacity. A faster fade suggests lower opacity or lower ejecta mass. A sustained plateau suggests ongoing energy injection. Another payoff arrives. These afterglows tie nuclear physics to visible light through opacity and heat diffusion, even when the core remains unseen. The scale shift returns softly. The arrangement of electrons in heavy atoms, a microscopic property, can control how long a cosmic glow lingers across days. Those days trace an event whose inspiral lasts millions of years. The scene eases back to the expanding veil. The front edge continues outward. The debris band slowly thins. The central region becomes quieter. The next step moves from aftermath to long-lived populations. Attention shifts to how neutron stars spin down, cool, and fade over time, and what that reveals about their internal composition and magnetic history. A neutron star can fade without ever becoming quiet because spin and magnetism continue to shape its signals. The long arc of spin down turns a fast rotator into a slower one while preserving the same compact core. At this distance, a lone neutron star sits in darkness with a faint surrounding haze. The surface glow is thin and steady. The magnetosphere is suggested as a sparse envelope with curved strands. The early anchor settles quickly. Spin down connects measurable timing changes to magnetic strength energy loss and the star's gradual cooling. The section holds three concepts. The first is spin down, the slow increase of rotation period over time. The second is braking torque, the mechanism that removes rotational energy. The third is thermal cooling, the loss of internal heat through radiation and neutrinos. Spin down is the gradual slowing of a rotating object, like a toy top that keeps turning while its wobble grows and its pace eases, rotation decreases as energy leaks away. Like a flywheel that loses speed when friction is present, the stored motion drains into the environment. This matters because timing can reveal how strongly the magnetosphere couples to space. The main visual anchor forms as a steady lighthouse-like beam pattern, without direct address or human imagery. A narrow cone of emission sweeps around the star. The cone is not seen as light. It is seen as a moving region of brightness on an imaginary sphere around the star. Each sweep traces a circular arc. The arc has a sharp leading edge and a softer trailing edge. The sharp edge is a boundary where conditions change. The trailing edge fades as particles thin out. The physical detail that holds the scene is that boundary and gradient. Over many rotations, the arc remains stable. Over long time, the arc slowly shifts. A small payoff arrives. Even when pulses remain regular, the spacing between them can lengthen by tiny amounts. That lengthening reveals a slow drain of rotational energy. The journey moves through checkpoints of cause and consequence. First is the torque from the magnetic field. The star's rotating field can accelerate charged particles in the magnetosphere. Those particles carry energy away. The torque depends on field strength and geometry. A stronger field can produce a stronger braking effect. A misaligned field can create a larger time-varying component. The timing signature is slow and smooth. Another visual anchor appears within the main scene kept distinct. Around the star, a thin halo of plasma forms a faint spiral pattern. The spiral is not a disk. It is a set of gently curving lines that wrap outward and fade. The lines are densest near the star. They thin with radius. Another payoff settles. The shape of the magnetosphere influences not only pulse shape, but also how efficiently the star sheds rotational energy. The section then links spin down to heat. As rotation energy decreases, some of that energy can heat magnetospheric regions. Meanwhile, the interior cools. Cooling proceeds by neutrino emission from the core early on, and by photon emission from the surface later. The surface temperature and hotspot patterns can change. Those patterns can modulate X-ray emission even when radio pulses fade. One number anchors the long timescale safely. Many pulsars remain active for about 10 million years. That is like a shoreline being shaped by slow waves over a geological era, each wave small yet persistent. The scale shift is gentle. Millisecond pulses at the start of life can stretch into second-scale periods over millions of years. The star remains compact throughout. Only timing changes. The main visual anchor deepens by adding a slow drift. The sweeping arc on the imaginary sphere widens slightly as the emission geometry evolves. The boundary becomes less sharp. The trailing gradient becomes longer. This suggests weakening particle acceleration. Another payoff arrives. A broadening pulse can indicate changing emission altitude or changing plasma density, not merely a loss of stability. The journey then approaches the middle age regime where many stars cross a threshold. At some point, the conditions for coherent radio emission can fail. The star can become radio quiet while remaining thermally visible for longer. The section stays calm. It treats this as a gentle fade rather than a switch. In that region, a signal would shift from sharp pulses to a smoother glow. Another payoff settles. The absence of radio pulses does not mean the star is inert. It can still cool. It can still carry a magnetic field. It can still reveal radius through thermal spectra under favourable conditions. Here the limit of observation is stated clearly. Spin-down age is not a direct clock. It is inferred from current period and period derivative. That inference assumes a breaking model. Real stars can have changing field strength, changing alignment, and episodes of torque variation. Glitches can also reset timing in small steps. Cooling curves are also uncertain. Surface emission depends on atmosphere composition and magnetic channeling. The limitation is that timing and temperature each rely on models with hidden parameters, yet trends remain informative. A rapid spin down suggests strong braking torque. A hot surface at a given inferred age suggests either slower cooling or ongoing heating. Another payoff arrives. Comparing populations of pulsars across periods and temperatures can map broad regions of interior behaviour even when each object is ambiguous. The scale shift returns softly. Particle motions near the star occur on microsecond scales. Their integrated effect slows a star over millions of years. The same star loses heat over comparable spans, drifting from bright thermal glow to faint emission. The scene eases back to the lone star and its fading halo. The spiral lines thin. The sweeping arc becomes softer. The next step moves toward the most magnetic outliers. Attention shifts to magnetars where braking, heating and bursts all become more extreme yet still traceable through calm physical signatures. Some neutron stars carry magnetic fields so strong that heat and stress become part of the signal even when rotation is slow. In these cases, magnetic energy can power persistent emission and occasional outbursts without relying on rapid spin. At this distance, a magnetar sits as a small dark sphere with a faint uneven glow. The glow is not uniform. It is patchy like islands of warmth on a cold surface. The early anchor is steady. Magnetars reveal how extreme magnetic fields deform crusts, heat surfaces, and reshape surrounding plasma in ways that timing and spectra can constrain. The section holds three concepts. The first is magnetic field decay, the gradual loss and rearrangement of magnetic energy. The second is crustal stress, the strain that builds in the solid outer layer. The third is resonant scattering, the way photons interact with magnetospheric particles along field lines. Resonant scattering is photon deflection at energies matching particle motion. Like wind chimes that respond only to certain notes, a magnetosphere can strongly affect only certain photon energies. Like a hallway of mirrors that redirects a lamp into a soft maze, scattering changes direction and spreads brightness. This matters because it reshapes the spectrum and pulse profile without changing the underlying heat source. The main visual anchor forms as a cracked cooling glaze. The surface is imagined as a dark ceramic shell. Across it, faint lines form a network of stress. The lines are not glowing lava, they are subtle seams. Around one region the seams cluster. The cluster outlines a rough oval patch. Inside the patch, the glow is slightly brighter. The physical detail is the boundary between warm patch and cooler surroundings. It is a gradient, not a sharp edge. The gradient suggests heat flowing through the crust. A small payoff arrives. A patchy surface can produce pulses even when spin is slow because brightness is uneven across the rotating sphere. The journey moves through checkpoints. First is the energy reservoir. In a magnetar, magnetic energy can exceed rotational energy. Decay and rearrangement can heat the crust and drive currents in the magnetosphere. This supports persistent X-ray emission. The glow remains steady for long periods, yet the crust is solid. Stress can build as the field shifts. The next checkpoint is crustal stress and release. Crustal stress is strain stored in a solid outer layer. Like dried mud that develops cracks as it shrinks, the crust can fracture when stress exceeds strength. Like ice that forms pressure ridges when pushed, the crust can buckle and slip. This matters because sudden rearrangements can inject energy into the magnetosphere and alter emission. Another visual anchor appears within the main scene, kept distinct. Along a seam cluster, a brief brightening spreads across the warm patch. It is not a flash of light. It is a gentle rise and fall in surface glow. The glow spreads like warmth, moving through a thick blanket. It rises, it peaks, it relaxes. Another payoff settles. Even a modest crustal shift can alter the magnetosphere. That alteration can change pulse shapes and spectra in a way that traces field geometry. One number anchors the timescale of the most dramatic releases without overstating. Some outbursts can last about a few minutes in their brightest phase. That is like a short rain squall, passing over a quiet sea, intense in the moment, yet quickly giving way to calmer conditions. The scale shift is gentle. A few minutes of enhanced emission can be followed by months of slow cooling. The brief event sits on top of a long relaxation. The main visual anchor deepens by extending outward. Curved field lines are suggested as faint arcs above the surface. The arcs rise from the warm patch and bend back toward the star. Along the arcs, a haze of particles forms a thin sheath. The sheath is densest near the foot points. It thins with altitude. The physical detail is a layered magnetosphere. Close to the star, scattering is strong. Farther out it becomes weak. Another payoff arrives. Resonant scattering can shift photons in energy and direction, creating a softer tail and broader pulses. This can mimic changes in surface temperature if not modelled carefully. The journey then approaches magnetic field decay as a slow driver. A magnetar's field can untwist over time. Currents can dissipate. Heat can leak from the crust into space. The warm patch can shrink, or it can migrate as stresses redistribute. In that region, light behaves as both messenger and participant. Photons leaving the surface pass through plasma that can redirect them. The observed signal is shaped by both surface and magnetosphere. Another payoff settles. Comparing pulse shape changes before and after an outburst can separate surface heating from scattering changes, at least in broad strokes. Here the limit of observation is stated clearly. Magnetar emission is complex. Multiple processes overlap. Surface temperature, atmospheric composition, and magnetospheric scattering can trade off in spectral fits. Timing changes can be influenced by variable torque from changing plasma loads. The limitation is that several different physical pictures can reproduce similar light curves. Even when strong clues exist, precise disentanglement can be difficult without wideband data and long monitoring. Yet robust signatures remain. A sudden spectral hardening with pulse shape change suggests increased magnetospheric scattering. A slow decay back to a cooler spectrum suggests crustal cooling after heating. Another payoff arrives. Magnetars provide a natural laboratory for ultra-strong fields because their signals carry both thermal and magnetic fingerprints. The scale shift returns softly. Microscopic lattice imperfections in the crust influence where stress concentrates. That stress can affect emission visible across thousands of light years. The scene eases back to the cracked ceramic shell and the faint arcs above it. The warm patch continues to glow quietly. The seams remain. The arcs fade into the surrounding dark. The next step moves away from extremes toward resolution. Attention shifts to how all neutron star classes fit together and how their signals form a calm map of dense matter without needing direct contact or direct images. A neutron star never becomes simple, yet its signals can be arranged into a calm map of cause and effect. Each class, from radio pulsars to magnetars to merger remnants, is a different posture of the same dense object. At this distance, the scene is a quiet panorama. Several neutron stars appear as small points within a broad field of dust and faint gas. No point is large. Each has a distinct rhythm and colour of glow. The early anchor is gentle. The shared physics is compactness, rotation, and magnetic structure. The differences are which reservoir dominates at a given time. The section holds three concepts. The first is compactness, the extreme ratio of mass to size that shapes gravity and light. The second is equation of state, the relationship between pressure and density in the interior. The third is multi-messenger consistency, the way different signals must agree on the same underlying object. Compactness is how strongly gravity is packed into a small space. Like a heavy stone placed on a soft cushion, the surface sinks deeply and shapes the surrounding fabric. Like a tight knot in a stretched thread, the knot changes tension far from its center. This matters because compactness controls redshift binding energy and the star's radius for a given mass. The main visual anchor forms as a slow-turning atlas. The atlas is not paper. It is an imagined sphere of faint lines and soft markers surrounding each star. Each marker corresponds to a type of signal. A narrow band indicates pulse timing. A wider haze indicates thermal emission. A faint ripple ring indicates gravitational wave memory of a merger. The atlas turns slowly, aligning these markers into one coherent picture. The physical detail that holds the image is alignment. When markers overlap, a consistent model exists. When they drift apart, assumptions must change. A small payoff arrives. The equation of state is not read directly. It is constrained by requiring that mass radius tidal deformability and cooling behavior can coexist in one interior. The journey moves through checkpoints of how constraints are built. First is timing. Period and its drift reveal braking and magnetic geometry. Second is thermal glow. Surface temperature and hotspot patterns hint at cooling speed and crustal channeling. Third is merger information. Tidal effects during spiral reflect how easily the star deforms, which depends on the internal stiffness. These are separate windows, yet they must refer to the same object. Another visual anchor appears within the main scene, kept distinct. Around one star, a thin ring of light appears slightly offset from the center. The ring is not a disk. It is a faint halo created by light bending near the surface. The inner edge is sharper. The outer edge fades. The gradient across the halo suggests gravitational curvature. Another payoff settles. Light bending can hide or reveal hotspots. This can change inferred radius unless compactness is modeled. The journey then approaches the equation of state with minimal jargon. It is a rulebook for how matter resists compression at extreme density. Stiffer matter supports a larger radius for a given mass. Softer matter allows more compression and a smaller radius. The interior cannot be sampled directly, yet signals reflect it. If cooling is unusually fast, it can suggest enhanced neutrino processes or exotic phases. If tidal deformability is low, it can suggest compactness and softer pressure support. One number anchors the scale in a safe and familiar way. The neutron star's radius is about 10 to 15 kilometers. That is like a large city across yet containing more mass than the Sun. The scale shift is calm. A city-sized object shapes space-time over thousands of kilometers around it. Its internal microphysics shapes signals that travel across the galaxy. The main visual anchor deepens as the atlas continues turning. Markers settle into a tighter cluster for one star. For another star, markers spread slightly. This conveys uncertainty without drama. The reason for spread is not chaos. It is incomplete information. Another payoff arrives. Agreement across signals is strongest when independent methods overlap. Timing, thermal emission, and merger constraints can cross-check one another. The section then addresses limits of intuition and observation with clarity. The interior is hidden behind an atmosphere and extreme gravity. Many measurements are indirect. Distance uncertainty affects luminosity. Atmospheric composition affects inferred temperature and radius. Magnetic fields affect spectra through scattering and anisotropic emission. In merger events, viewing angle and ejecta properties affect electromagnetic interpretation. The limitation is degeneracy. Different parameter combinations can mimic the same observed signal. Models can fit data while representing different interiors, yet constraints still narrow. A model must satisfy multiple conditions at once. Another payoff settles. Uncertainty does not erase information, it bounds it. When several signals point toward the same compactness range, the allowed interiors shrink, even if the exact answer remains unknown. The journey then softens into a final perspective. Neutron stars occupy a middle ground between atomic nuclei and black holes. They are laboratories where quantum behavior and gravity meet. Their signals are slow to interpret but steady in their rules. The scale shift returns gently. The arrangement of neutrons and protons deep in the core influences pulse timing measured over decades. Those decades are short next to a star's lifetime, yet they are long enough to reveal drift. Another visual anchor appears near the end as a calm closure. The panorama of points fades into a single point. The point remains. Its glow steadies. The surrounding dust becomes a soft gradient. Another payoff arrives. In the end, the most useful picture is not a dramatic event. It is the quiet persistence of measurable change. A signal would continue to arrive. It would carry the imprint of compactness, stiffness, and magnetic structure. The final transition is gentle. The atlas turns more slowly, the markers dim. The scene settles into darkness that remains calm with no new question opened.